You know, when we think of a solid, we usually picture something hard, something unchanging, right? Like a rock or a chunk of metal. But if you could zoom all the way down to the atomic level, you'd see that the world of solids is this incredible battleground between perfect, beautiful order and just total chaos. Not all solids are built the same, and their biggest secrets are all hidden in how their atoms are arranged.
So you can basically split the entire world of solids into two huge camps. On one side, you have these perfect repeating patterns, and on the other, you have complete and utter randomness. And this one single difference, this is the key to understanding everything. It's why glass shatters but metal bends. It's why diamond is one of the hardest things we know, while something like wax is so soft. And this slide just illustrates that divide perfectly. Over on the left, we've got order. That's a crystalline solid, like quartz. Its atoms are lined up in this definite repeating pattern, almost like soldiers in perfect formation. Then, on the right, you've got chaos. That's an amorphous solid, like glass. Its particles are just a jumbled mess, with no real long-range order at all. And here's the craziest part. Both quartz and glass are made of the exact same stuff, silicon dioxide. It just goes to show you, arrangement is everything.
So let's get a little more specific. A crystalline solid has this beautiful, predictable internal structure. I want you to imagine a library where every single book is in its exact, designated spot on the shelf. That perfect organization is what gives materials like salt and metals their really unique and consistent properties.
Amorphous solids, on the other hand, are the complete opposite. They're like that same library, but after a big earthquake, books are just everywhere. The particles are frozen in place, sure, but in a completely random, jumbled-up arrangement. Candle wax is a perfect example. It's made of these huge hydrocarbon molecules that are just too big and tangled to ever line up in a neat pattern as they cool down and solidify.
Okay, now this is where it gets really interesting. This internal structure has a huge effect on how these things melt. A crystalline solid melts at one single, precise temperature. So why is that? Well, think about it. In that perfect structure, all the bonds holding it together have the same strength. They all need the same amount of energy to break, so poof, they all let go at the exact same time. But amorphous solids? They just get softer and softer over a whole range of temperatures, as their weaker, jumbled bonds break first, and then the stronger ones follow.
All right, so for the rest of this explainer, we're going to leave chaos behind for a bit and focus entirely on the world of order. Because even inside the perfectly structured world of crystals, there are four really distinct families, and each one is held together in a totally different way.
And here they are: ionic, metallic, covalent network, and molecular solids. You know, understanding these four types is kind of like having the master key to the properties of pretty much every crystalline material on Earth. So let's use this as our roadmap and break them down one by one.
Okay, let's dive right in with our first two types. And these are all about the incredibly powerful forces that get generated by charged particles and these amazing free-flowing electrons. First up, we've got ionic solids. The best example? Just think of regular table salt. It's made of positive sodium ions and negative chloride ions, all locked into this super rigid, alternating grid. These opposite charges are powerfully attracted to each other, creating these incredibly strong bonds that just lock the whole crystal together.
Okay, so those super strong bonds, well, they explain the really high melting points. But why are they brittle? This part is so cool. If you hit an ionic crystal hard enough, you can shift the layers just a tiny bit. But now, all of a sudden, positive ions are lined up next to other positive ions and negative next to negative. They repel each other like crazy and bam, the whole crystal just shatters. And they only conduct electricity when they're melted or dissolved because that's the only time the ions are actually free to move around and carry a current.
All right, next up we have metallic solids, like copper. And the key concept here is just fantastic. You've got this fixed grid of positive atomic nuclei, but their outer electrons, well, they aren't attached to any single atom. Instead, they form this sea of electrons that just flows freely throughout the entire structure. And this sea of electrons, that is the secret sauce for all the classic properties of metal. It's why they're malleable, you can bend them because the atoms can slide past each other, but that electron sea just flows right around them, holding the whole thing together. It's also why they're such amazing conductors. That sea is basically a superhighway for carrying heat and electrical charge from one end to the other.
Okay, let's move on to our next pair. And here we're going to see how a different kind of bonding, sharing electrons, creates both the absolute hardest substances known to man and also some of the softest.
So covalent network solids are basically the titans of the solid world. In a material like diamond, every single carbon atom is covalently bonded to all of its neighbors. There are no separate molecules here. The entire crystal is essentially one massive interconnected molecule.
And the result of that structure is just staggering. To melt a diamond, you don't just have to weaken some forces. You have to physically break those incredibly strong covalent bonds throughout the entire network. That takes a colossal amount of energy, which is why you get that extreme hardness and that just astronomical melting point.
And finally, we get to molecular solids. Now listen closely because this distinction is absolutely crucial. In a solid like ice, you have individual neutral molecules, in this case, H2O. Now the covalent bonds inside each water molecule are really strong, but the forces holding one water molecule to the next one, those are much, much weaker.
And that is why these solids tend to have pretty low melting points. See, when you melt ice, you're not breaking the strong bonds inside the H2O molecules themselves, you're just overcoming the weak little attractions between them. That's a much, much easier job to do, which is why ice melts at 0 degrees Celsius, not 3,500.
So when you put it all together and look at it side by side, the pattern becomes crystal clear, right? A material's properties, how it behaves, can be traced directly back to what its particles are and what kinds of forces are holding them together. From the super strong ionic bonds in salt to the weak intermolecular forces in sugar, the story is written right there in its structure. Okay, now that we've got the fundamentals down, let's look at a mind-blowing, real-world example of this in action. Because understanding these structures isn't just an academic exercise, it's what lets us discover and engineer totally revolutionary new materials.
So here's a thought experiment for you. What if you could take a covalent network solid, like the graphite in a pencil, and somehow peel it apart until you had a sheet that was only a single atom thick? What kind of crazy properties would something like that even have?
Well, believe it or not, back in 2004, that is exactly what two scientists did. Using literally nothing more than a block of graphite and some Scotch tape, they actually managed to isolate graphene, a one-atom-thick sheet of carbon. This ridiculously simple act of discovery won them the Nobel Prize, and it unlocked a material that's super strong, incredibly lightweight, and an amazing conductor of both heat and electricity.
But, all right, here is the final kind of counterintuitive twist. After all this talk about perfect, beautiful, repeating patterns, it turns out that sometimes the most useful crystals are the ones that are intentionally flawed.
These are called crystal defects. We're talking about things like an empty spot where an atom should be, or an extra atom squeezed in where it doesn't belong. But the most important one is an impurity, where a foreign atom replaces one of the original ones. This process, called doping, is the absolute foundation of our entire modern electronics industry. By intentionally adding tiny impurities to silicon crystals, we can precisely control their electrical properties to create the semiconductors that are in every single computer chip on the planet.
So when you really think about it, from the perfect order of a diamond to the controlled, engineered chaos inside a computer chip, our entire world is built on understanding the solid state of matter. And as our ability to control these structures grows, atom by atom, it really just leaves you with one big question. What are we going to build with them next?